Hi everyone. What we're going to talk about today are a couple of features that are valuable for some of the 5G requirements that are coming out with antennas. Now, if you haven't heard of 5G, it is coming and it will be huge. It's going to change Earth as we know it, bring world peace, angels will be singing, and all things will be possible. Now, to enable this kind of bandwidth and data rates, we're going to have to do a lot of things in the RF and microwave communities, including antennas. And so these antennas are going to have to become very highly directive to save power and in order to get things localized well. So what we're thinking of is things like phased arrays for the antennas, where we're steering the beams, multiple input, multiple output kinds of technologies. Now, if you're going to make these kinds of antennas, you obviously have to, of course, have obviously good EM software, good antenna engineers designing them. But we at AWR with Microwave Office have to enable a couple features to support this too. And I want to talk about a couple of those today. So we're not actually going to talk about the EM today for the antennas. Rather, we're going to talk about the circuit and system requirements. So let's think about this for a minute. If you're going to support antennas at a circuit level, meaning you've run the EM simulation, and you now, of course, need to excite the antenna, excite the S parameter file, a couple of things jump up at you. And in particular, I'm going to talk about today something called in situ antenna issues with circuit simulators. In a nutshell, as we get into it, here's the problem. You have an antenna array, and of course you're going to steer the array by changing the inputs, the power into the inputs, their power level and the relative phasing, and this is what steers the beam. This is how we steer an antenna beam. Well, that power is coming from power amps, and the trouble is the power amps are affected heavily by the load impedance, which is the same as the input impedance to the antenna port, and so they affect each other, the power amp and the beam. As you steer the beam, the loads change. As the loads change, you're going to change the performance of the power amps. So they're really coupled together, and it is not sufficient to just run the EM and look at the antenna pattern, because it's not going to involve the power amp. So that's in situ type problems. I'm going to show you what our solution is in version 12 of Microwave Office. Another thing I want to show you today is at the system level, and in particular in our system simulator, VSS, Visual System Simulator. Again, you probably want to include array effects, and we have a new element in VSS, which is an array element. It basically uses the array equations, and it has a number of nice features to it, which I'll be getting into. Once you have this element, you of course can look at the array effects, you can look at propagation effects, etc. So we're going to take a look at both of these guys today and see how they work. All right, let's get going with the antenna. As I already mentioned, typically this is a problem when we have multiple inputs to our antenna. Now usually that's a phased array, but you also actually have antennas. They're a single antenna with multiple inputs. They're either changing the polarization or possibly the beam somehow. And these are typical antennas used in communication systems. We're going to see a lot more of them in 5G applications. Again, the antenna is going to affect the power amps feeding the antenna. And of course, the power amps then will change their performance, which will change the beam. We have to couple these together. Let's take a look at a simple example of how this works in Microwave Office, and I think you'll get the idea. How did we used to do this? Well, the way people did it is on the left is the antenna array. You, of course, have to EM it, and you get an S parameter file. Our example is a 4x4 patch array, so we have 16 ports. Then, of course, in a circuit schematic, you're going to have the feed network, which you see in the middle there, and then you're going to feed those guys with an amplifier on the right. So you have to have all these components in the simulation. Now, the way it used to work again is what happened was the designer would get the S parameters from the EM. Step 2, they would look at the beam they wanted. So they would just go ahead and excite the various ports, essentially in the EM visualization. They would read off the impedance, and then they would have to go to the circuit simulator, put that impedance in, run the power amp simulations, see what the impedance should have been, and go back and forth iterating. You can do it, but it's really a pain to do. So what this new in situ feature does is it automates that process. So let's take a look at how it works. So first of all, you still have to run the EM. We're sorry, folks, but you still have to have S parameters of the antenna array. You only have to run it once, but you do have to run it. So we've got the antenna array, and then the next step is we go into the circuit schematic and we build up our, in this case, our feed network feeding the antenna. In this example here, you can see on the right the input to the array. This is a simple harmonic balance port. We're putting in a certain amount of power. And then we then start splitting things out, and you can see I've circled one of the Wilkinson dividers. There's several of these so that we eventually get down to the 4x4 array elements. As we zoom in, I'm showing you here on the left a typical element coming off the Wilkinson, and you see that transmit module. Let's dig into that for a minute. Picture on the right. You can see that you have an attenuator, which we control by equations. We have a phase shifter, which we also control by equations. These are what is going to steer the beam. And the thing that is new is you'll notice that subcircuit is actually literally a mimic amplifier. It's a power amplifier. And we're putting 16 power amplifiers into the simulation. Again, they will feed the antenna elements. The impedance of those elements, the input impedances into the antennas, are the loads of the power amps. And as they change, as the beam steers, they're going to affect the power amplifier performance. I'll just show you some results from this very quickly. This is essentially load pull, and obviously we want to get the maximum power delivered to the antenna elements. So what we have on this graph is you're seeing maximum power out with the green circles. Of course, you want the maximum power you can get in the middle there. And then the purple circle is the various load impedances of the antennas as we scan the beam. And what the engineer is doing here is trying to achieve some sort of compromise as they go through this in situ simulation. How does the EM simulation know where the power amp is? And for those of you familiar with Microwave Office, it's quite simple. The critical thing here is if you look at the measurement dialog box here on the left, you'll see we're using harmonic balance, the nonlinear simulator, and asking for the power in this antenna pattern. And notice on the right, that second box down says excitation circuit. Well, that is literally the schematic that you're putting the S parameter file in of the antenna measurements. And it then knows where the power amps are that are exciting it. So that's how we couple them together. And then the graph on the right, you can actually literally see the power coming out of the antenna, again with the power amps included. Couple nice pictures here for you. You can see that the beam, of course, is steered as we change the phase of the various elements, as we change the attenuation. We change the phase in both the theta direction and the phi direction. And you can see the beam is steering. The side lobes are varying, etc., as we expected. Again, the important point is the power amps, the power out of the amps and the coupling is now included in these pictures. Final thing I'll say on this one is if you can tune something like our phase and amplitude, you can optimize. And this is a quick example of optimization for these antennas. We are going ahead and optimizing over the phase and attenuation to the various elements. And this engineer is trying to optimize the pattern to be a certain, in a certain direction, actually, with certain side lobes. And you can see the blue optimization bars. You have to get underneath those. And as that optimizes, of course, the pattern changes. Again, if you want, you can include the effects of the power amplifier as you're doing this. Okay, so to conclude, you have to couple the power amp, the nonlinear stuff, to the antenna pattern because they affect each other. And with in situ, we can now do that. Let's move on to the element I was talking about in the system simulator in VSS and take a quick look at that. Again, we're thinking phased arrays here, and what this element does, this model, is essentially you set up the array equation, say how many elements you have in the array, the geometry of the array, and then it will use that effect, those equations, to calculate the propagation, the coupling, etc. You could have a transmitter or a receiver, for example, and you can throw that into your system simulation. So let's see some examples of this. First of all, you can pick different types of array layouts, and you can see we have rectangular and some more exotic arrays. As a matter of fact, you can even do a pseudo-random array if you want to. Here's what it looks like in VSS. I have it circled. It's just an element in VSS. Of course, behind this is a control panel with a lot of settings, setting things like the number of elements, etc. Incidentally, you do not have to use ideal dipole patterns. You actually can use a pattern coming from an EM simulator, either Axiom or Analyst. And so you could actually use a real pattern for one element, say one patch or one horn in your array. And then as you array them, it will use that pattern superimposed with the array equation. So you can actually get the effects here of real antenna patterns in this too. Now, of course, you excite this thing, you can excite it with various input data, as simple as a sine wave and as complicated as various communication type standards. Here's another example. This is a rectangular array. You can see the pattern below you on the lower left and in polar form on the right, and you can go ahead and steer this array. You could have a transmitter, a receiver, and go ahead and figure it out. Notice this is using a Dolf-Chebyshev type taper, fairly typical, and you can set all these things in this element. You can actually take some of the elements and turn them off. In other words, you're simulating array failure type scenarios. You want to see how much the pattern degrades, how many elements you can tolerate before the pattern becomes unacceptable. You see here on the left a failure rate of 2% chosen randomly, and a failure rate on the right of 5%. And of course you can see the pattern degrading. So in conclusion, in the system simulator, we now have the capability of including array effects with this new model. You can even include actual antenna patterns from a given element of the array if you want to make it more accurate. We're currently working on coupling between array elements, which will give us even more accuracy in the system simulator. So I'm out of time, folks. I hope you enjoyed this video. And again, what we've got here is some new features to help you with your antenna simulations as you look into 5G applications. Thanks a lot.